Welcome. My name is Rachel. I am the Market Development Manager at StatEase. And for StatEase's 40th anniversary this year, we have organized a very special webinar for you today, Developments in DOE, a panel discussion with five experts on the topic. So if our experts could please introduce themselves, we can start with Márcia.
Hello, everyone. It's really a pleasure to be here. Thank you for the invitation. And I'm Márcia Breitkreitz. Currently, I am a university professor. I work at State University of Campinas, Unicamp, in Chemistry Institute and Pharmaceutical faculty as well. So my major interests are related to chemometrics, including DOE, for product, process, and analytical method development, especially in the pharmaceutical area. So I have trained many industry professionals over the past 15 years. And also I teach undergraduate and graduate students in the university. So in a nutshell, I am a professor and passionate about DOE, especially in pharma development.
Thank you. Gamal?
Hi, good morning, everybody. My name is Gamal Weheba. I'm a professor of industrial engineering here at Wichita State University. This is in Kansas, USA. I've been with Wichita State over the last 25 years, and I teach industrial engineering topics, including the design of experiments. My focus is always on manufacturing, especially composite manufacturing, that is very important for the aircraft industry around us. It's centered here in Wichita, and we do also a lot of applications in the medical field. I'm so happy to be here, and thank you for the invitation.
And Geoff?
Hi, I'm Geoff Vining. I'm a recently retired professor of statistics at Virginia Tech. I've got a lot of experience working with people. I've got a jet turbine example I'll talk about a little bit today. I cannot mention the company because it'll get me in trouble, but I've done a lot of work with NASA and with the Department of Defense. My area historically has been planning experiments to improve quality, productivity, and reliability.
Thank you. Drew?
Yes, good morning. I'm Drew Landman from Old Dominion University. I'm a professor in the Department of Mechanical and Aerospace Engineering. My background is in wind tunnel testing, and I got into DOE and RSM really because I saw the benefits to using it. And we have had this giant cultural bias in our discipline against formal experiment design for some reason. So 20 years ago, we started to educate engineers in this area as part of our graduate program. And now we have a lot of engineers in the field, and we're slowly changing that cultural bias. And I'm happy to be part of it.
Thank you. And Arved?
Arved, you're on mute.
Now I'm unmuted. I have a master's degree in statistics from Virginia Tech, went to school with Geoff, and I'm a consulting industrial statistician at Eastman Chemical Company in Kingsport, Tennessee. And I'm doing what I was hired to do 37 years ago. So I'm a rare bird in doing what I was hired to do. And especially do a lot of different kinds of statistics in practice, and especially design of experiments.
Thank you, everybody. So we have a few topics that we're going to go over today. Our experts are going to talk for about 45-ish minutes, and then we'll have 10 to 15 minutes for Q&A at the end. Feel free to ask your questions whenever by putting them into the chat. I will gather them and present them to the panelists at the end. For our first topic, what can you talk about with regards to best practices in DOE for industry or in your specific industry?
Well, I think I can start with that one because I've been teaching DOE for industry for over 15 years now. And as I said, I work mainly in pharmaceutical, product process, and method development. So I'll discuss a little bit about pharmaceutical scenario, and you feel free to contribute anytime. And so I can say that in the pharmaceutical scenario, the quality by design and analytical quality by design strategies have motivated and helped organizing the use of DOE for industrial purposes. That was a really mark on the use of DOE. Since these strategies, they brought together the risk analysis and the multivariate thinking. So some important points that I would like to highlight here. Based on the risk analysis, we can answer some questions for the pharmaceutical development. Which variables are worth studying? Which are the most risky? How many variables do we have? And what do we know about them? I think this organizing this thinking is very important to select the proper DOE method to carry out the study. So this helps to select if we're going to use a screening method, a characterization method, an optimization method. And I see many confusions in this point, especially related to selection of screening DOE methods. Sometimes people select the wrong screening methods, so they don't get the right responses. For example, selection of resolution 3 designs is not really suitable for a screening study at the beginning of the study. And I see that very often. So it would rather be useful resolution 4 or, if possible, resolution 5. I see some opportunities for the use of DOE within the quality by design framework. So I think that the regulatory agencies, they made clear that DOE is a useful and necessary tool. And the pharma companies now, they have to think where are the opportunities to use each method. Formulation development, process development. In this case, we have to think about the scale-up issues, and we have to think about also about raw material inclusion, the study of raw material, the material attributes in each study. I think this is a major point for pharmaceutical development. We have an IPEC guideline for excipients, quality by design for excipients at this point. And this is a major issue that I see pharma companies are facing at this moment to use DOE. So they have to think about possible interactions. So interactions of raw material attributes, variability of raw material, it's a major point for pharma companies. I'll talk a little bit about that later. Formulation development itself and how to include the variability of raw materials into process development so that the process can accommodate variability of raw materials. So these are, in my opinion, this is mature thinking on where to use DOE within the whole pharmaceutical development. Companies have to think about that at this moment. And the interactions, at this point, I still see that people are not really familiar with interactions, and we see interactions between raw material formulation and process variables. So it's mandatory the use of DOE. And I think that's a big difference between using DOE in an academic scenario and industrial scenario. The big difference is related actually to the inclusion of uncertainties of input variables that we use in our DOE. When we are developing.
I saw some head nods from Arved and Gamal. Is there something similar or different in your industry?
Yes, the planning parts that she's mentioning is a very critical piece and involving the subject matter experts in the planning and having, well, one of the things I heard at a recent conference is the collaboration ideas of a statistician expert with the subject matter experts and them collaborating together, not just in a consulting environment, but even coming together, helps self-educating each other, helping with that. Another thing I'll mention along with the specific best practices that we've seen lately in the last several years is split plot designs are used a lot more than they were previously due to software and other reasons, but they are better understood and the software has finally caught up with what can be done, and it's a fantastic addition to be able to set experiments up properly for the processes.
Yeah, that's true.
As a quick follow-up to what
same,
Arved said, the notion of collaboration with the subject matter experts is absolutely critical for advancing how we should be doing DOEs, just universally. And we haven't done enough of that. You know, this is one of those things where you really have got to get the interactions between all of the experts in the room and learn a common language. And that's what the future is going to have to become.
In the pharmaceutical industry, I'm just curious, do you use split plots a lot? Do you have pushback against fully randomized designs, or is it easy to typically do a fully randomized design?
No, actually, I had my master's dissertation on split plot designs, but for industrial applications, I haven't used it much.
You haven't? Okay.
No.
And what we're
Normally,
finding in aerospace testing is that we almost have to use split plots. There's so much pushback in so-called wasting time randomizing, which of course we'd rather do, but that's interesting comparison.
I think there's a whole lot more opportunity to use split plots. People are overlooking, like I did early in my career. I'm working on one now with, it's a big experiment. 8 factors, 4 are hard to change. And that's real, that's reality.
With aerospace testing, particularly with the new vehicles that are coming out, such as the urban air mobility vehicles, if you've seen them, they have as many as 20 factors. And they're trying to characterize those in a wind tunnel study with all those factors being varied. And this has really driven us not only to split plot, but just to DOE in general, because I don't see how you unravel that with a 1 factor at a time design. It's really changing our culture, I think.
yeah, that's not even possible. Something that I've realized over the time is that when we have categorical variable, split plot and completely randomized designs, they are equivalent for categorical factors because main plot error is small based on our experience here. But I think I won't develop that topic here.
I'll interject another best practice that's happened over recently with, again, the advent of the software has been the attitude that we're going to create a design that fits the process, not make the process fit the design. And so we are able to, with optimality designs now, there's many flexible type of designs out there with optimal designs, and with custom augmentation, with shifting, doing initial designs and shifting and expanding the design space. There is so much more flexibility to design the experiments properly for the processes than we used to have.
One aspect that I think we'd like to see improve in the future would be the ability to define constraints. It's fairly easy to define a linear constraint in the design space, but it'd be really nice if we even had a graphical constraint where you could just get over the top regions of disallowed factor settings.
Well, something that I still in this topic of best practices for using DOE for industry, something that I would like to highlight, that it's a big difference between developing a method for academic purposes and industrial purposes, is the establishment of uncertainties in the design space and method operable design region. These are key elements in quality by design, in analytical quality by design, and they are easily done by different software, both by overlay procedure and desirability functions. But something that I think it's quite new and important is the establishment of uncertainties, the limits of uncertainties, for us to establish a robust and correct and useful design space for industry, for everyday use, for example, in method development and on process development as well, realistic and robust design space. I have prepared a couple of slides, PowerPoint slides on that. If you could share,
Coming up
Rachel,
momentarily.
please.
Share. All right. Which slides would you like to see?
Yeah, the first one. This slides are just picked from a presentation. They are related to analytical method development on chromatography, liquid chromatography. These are just for me to highlight some points. So I'm talking about the importance of variability and incorporation of uncertainties of the input variables in design space and method operable design region. There are equivalent terms for analytical quality by design and quality by design. So we have different methods available on software to do that nowadays. One is Monte Carlo simulations, where we add the variability of input factors. In this example, I have 3 variables from chromatography. So we have this input variation. Normally, we don't take this into account, but we should. My point here is that we should. And by Monte Carlo simulations, the algorithm generates a distribution of the responses by combining each input setup, adding each input setup to the model, and then we have a distribution of the responses. So we don't have merely the average response, we have the distribution. And this is very, very important to establish the failure limit for industrial applications. And this is just computer calculations. We don't have to add any more runs. So the analysts can just add the variability of input variables. And in the next slide, I added, can you go to the next, please? Yes, another tool to do that, which are related to intervals. I think these are very important nowadays to have a robust design space. So the first graph shows in the yellow region a design space with no uncertainty interval. Then we have the second one with the confidence interval. And at the bottom on the left, prediction interval. And then in the bottom right, we have tolerance interval. So this is easily incorporated in StatEasy 360, and the calculations are there. And we can see we have a small region that are related to uncertainties, and they increase as we go from confidence to tolerance intervals. They have different meanings.
Yeah.
I'm not going to talk about that here.
This input uncertainty sounds like it would be present in manufacturing as well, not just in pharma.
It's ubiquitous. It's ubiquitous. It's everywhere. And it's important to be able to take that into account. But one of the things that concerns me about this is I think we failed to take advantage of ancillary information when it's available. We've not done a very good job with that in the past. But that's the future. We've got to do is to borrow some techniques from machine learning and from data science and adapt them to make them work so that we can begin to understand better what's happening with our system. Rachel, it might be good to show some of my slides. I think it was worth
Yeah, I
showing.
was about to say, do you want to talk a little more about that?
Yeah, I would, please.
Okay, I have to switch the sharing. Give me a moment. That one. Share. You said
Let's
slide
go to,
7?
I would like it's slide 7 or so. Yeah. I hope all the participants can get these slides, so originally this was set up for a longer conversation.
Oh, absolutely.
But the key here is I want to highlight a real problem. This is a massive problem. This is a jet turbine manufacturer who was losing $1 billion a year initially with the release of a jet turbine. Most people don't realize that the people who make jet turbines do not make money selling the turbine. They make it on the maintenance contract. They had a critical temperature they took too high. So then suddenly they had no idea how to deal with the situation. So the first step out of this, when we got a hold of this data, was can we start extracting the variability in the data? So Rachel, if you can go to the next one. On the left-hand side is the temperatures in degrees Celsius actually observed for one engine. So this was all the data for a particular engine. We had information on almost 200 engines. And that's a mess. Can you see anything that looks like degradation in there? It just like scatter everywhere. So far, so good. First step is how do we extract that information? How can we begin to see what's going on? Well, the logical first step is to involve the thermodynamics. It's a real simple system that runs a jet turbine. There are only two characteristics. Drew knows this better than I do. It's the inlet temperature and it's the pressure ratio. That drives everything. Now, if you assume ideal gas, you're in trouble. So we created a technique where we could treat that baby. But notice these are the residuals on the right, and you can begin to see the degradation pattern. And the only reason why you can see it is because we were smart on how to extract the extraneous variability. I hope I'm making sense. Drew, do you have any comments on this? You're muted.
You are on mute.
Thank you. I'm trying to understand what we're looking at. So we're looking at temperature versus time for a particular turbine run, like over one run, or is it over time, like years?
These are all individual flights. So what you're
Flight.
looking at
Okay.
is about 2 years worth of data.
Okay. So critical temperatures or highest temperatures measured during flight.
Well, of course, but you can't measure that high temperature. That's the problem here.
Yeah. Okay. Gotcha. Okay. All right.
So that's what's going on here. And all we're trying to do is extract some of that variability. But that's just with a thermodynamic model. So far, so good?
Mm-hmm.
Okay, let's go to the next slide, Rachel. On the left-hand side, we had ancillary information. So they've got sensors all over this jet turbine. And that's where I see the real opportunity for how we can enhance experimental design in the future, making intelligent use of this ancillary information. So there were hundreds of variables that we could look at. We cooperated with the engineers with this company, and we got it down to a manageable list. We were using things like MalloCP to come up with a model. But what you have here on this particular plot is when we use, I think it was 13 variables that were available to us to remove additional variability after we explained the thermodynamics. So far, so good. You know, notice we can begin to see the pattern a little bit better. We're beginning to see some outliers, and some of those outliers are actually interesting. You can tell there was a big maintenance cycle, just over 1,000. And you see a lot of those high points on the left-hand part of that plot. Turns out they have a common characteristic. It was the altitude of the airport, which impacted the initial temperature. And there are very few airports that are over 1 mile above sea level. All of those were much more than 1 mile over sea level. So we can begin to extract that information as well, which again allows us to be able to make more intelligent decisions. And the plot on the right is just the overlay of what we did with the ancillary variables relative to the thermodynamic model. And notice how much tighter we've got what's going on, and how much better we can begin to see how the degradation is occurring, which is the real characteristic of interest. We have to start thinking about how can we take advantage of these extra data in an intelligent fashion. I've got another example. I'm not going to talk about it, but it's in the notes in these slides. I'm working with some colleagues in Italy, and it's a battery decay problem. And we were able, by extracting the variability very simply, to get the error term to e to the minus 5. That's the error term. When you have e to the minus 5 as the error term for your measurements, you're seeing almost to the level of the deterministic system controlling it. And that's an important thought as well, because whenever we analyze data historically in statistics, we force things to be a hypothesis test. Hypothesis tests assume the data are independent and identically distributed. These are deterministic data. There is no way in God's green earth it's independent and identically distributed. And it turns out you don't need to do hypothesis tests. You don't need probability theory. And it winds up being a much simpler analysis. But in that sense, we're mimicking the data scientists and the machine learners. So that's one of my points that I want to make, is that we, in terms of being statisticians, trying to advance the future for how we analyze experiments, we need to be able to take advantage better of the information that is available to us. And we often use techniques that were almost outdated in the 50s, but they still dominate because they're focused on means. Means hide information. They don't explore information. So that's what I was hoping that we can begin to talk about here as a profession.
So yeah, that would be a great next topic. What are some cutting edge techniques involving AI or machine learning that are getting you these new insights?
For me, it's what I've been doing. I'd love to hear what other people think.
I'll chime in on a few things that I'm seeing out there. A big one is using DOEs on actually the hyperparameter tuning of the models. I've seen that a lot. That's one. There's lots of opportunity there. You're seeing neural nets, but there's opportunity for many hyperparameter tuning and many other models. I'm also seeing something that it just doesn't have a consistent name. It's called Bayesian optimization, sequential learning, active learning. It's taking a model developed with some of the AI type models and being able to recommend candidate runs to actually go out and produce more data. So it's almost like the old simplex optimization, but my analogy there, but it has a very fancy way of coming up with what the recommended next points would be to move you to optimization. And there is software out there doing some of this now, but there's a lot of work going on around it. That's a couple. I could list some more, but I'll let some other people chime in.
Well, I have just started working with GOE plus neural networks, so I don't have much expertise on that topic yet. But I think this combination would be really useful for us to understand more complicated systems where multiple linear regression is not quite efficient. So maybe I'll get back to this topic in the next anniversary of Studies.
I'm concerned about a lot of these techniques because they just throw parameters randomly into the models, and that in some sense is inefficient. We've developed a measure where we can actually compare some of the machine learning techniques to multiple linear regression. And it's a very simple adaptation of MalloCP, but reverses things a little bit. But the key to it then is, have you over-parameterized your system? Every time I see a presentation about machine learning neural nets, nobody cares about how many parameters there are, which then means you got a lot of junk in the model. What you would like to do is get the most parsimonious expression that you can. And that's been my biggest criticism of both neural nets, machine learning, artificial intelligence. People are wasting resources building huge models that perhaps there is a smaller model that would be equally as good and easier to understand and interpret.
Any other
The
thoughts?
other things around the AI models is they are predictive in nature. And I will say in the chemical industry, predicting is good, but many times we need to know the cause effect relationships. And knowing and understanding those cause effect relationships and then converting that into understanding what chemical reactions are really going on, just like Márcia was describing the interactions going on. Those are critical to gaining understanding about what's really happening. Being able to predict what's happening, that's good, but that's only a piece of it. And many times in the predictive models, we don't have that. There is a lot of work going on to try to come up with some ways to turn those, to get some cause effect relationships out of that. I would like to see a lot more work going on around that. And there's a lot of work around the SHAP values, shapely additive explanations that people are using out there to try to come up with ways to understand what the actual variables truly, which ones are truly affecting the models. But there's a lot of work to be done around that.
And highlight that the work that I was doing with the jet turbines, we could discover very quickly that we could take two engines, 250 flights each, and it would predict accurately the thermodynamics for the entire fleet. The entire fleet. It was huge predictive capability. Was there a unique model that did it? No, the collinearity was very extensive. There were 3 or 4 that did really parallel jobs with that. But what's exciting is if you could take, 500 flights and predict an entire fleet for 20 years, there's some real value there.
Jeff, are they using that data for mean time to overhaul?
We were trying to get it to the point where they could even use it to propose the maintenance contract. So the real objective to it was to have the predictive capability roughly for at least for the first few major maintenance cycles. So we were looking up to 4 big major maintenance cycles and then and be able to adjust it for routes.
Interesting.
One of the problems with it was this company, it was ITAR restricted. So we lost communication with the engineers. So we were never able to take it as far as we wanted to.
Understand.
I have a concern. I don't know. Maybe you guys can give your opinion. How do the regulatory agencies will see that for industrial applications? since we won't have this explicit cause and effect relationship. We might not have an explicit model like we have in multiple linear regression. What do you think about that? For example, using neural networks.
In my world, we have no regulators who are overlooking what we do. So there's a lot of freedom to do some interesting and sometimes crazy things.
Well, that's pretty good.
Gamal, did you have something to add about that? It looked like you were agreeing with Márcia about the regulators and the concerns.
I am. We, you know, what regulators would care for is the outcome. As we can see in aircraft industry, they set limits and let you work your system up to the required value. But my observations based on the aircraft industry around me, it's basically assembly, is that they tend to hesitate to kind of use design experiments because it requires some changes, and they're very sensitive to changes. They may be at ease using some SPC, statistical process control techniques, but the amount of learning you can get from SPC is really limited. If you want to accelerate learning, you really need DOE and the ability to cause changes to processes so you can understand interactions. Other than that, you will be left in the dark. So the fight here is always to convince them that the changes that will take place, are really minute, but they will actually help us understand the systems better. They love the idea of having some mathematical way of expressing or anticipating the outcome with good understanding of the causal factors in their processes, things that need to be controlled regardless. You really, with DOE, working with the process, not the product. The focus is always on the product, but in reality, what we care for is the process. I can tell that we're way from incorporating artificial intelligence in the work, given the fact that we have very limited data, and I would really be skeptic if somebody can claim knowledge to a level that they can start, improving a model that does not exist or cannot be trusted. This is my take on that. Thank you.
Make a couple quick comments before we move on about that. One is about this topic, and one is predictive models can oftentimes help us get to an optimum or close to an optimum. But when you get there, you need to look around and see where you're at. Are you on a cliff? Are you on a flat area? That's where the DOEs come in again. So they add values. Also, the idea of these digital twins that we're seeing and hearing about. I'm seeing people having these digital twins, but they're these computer models, but they don't really understand what's going on inside of those. Again, you can run DOE computer experiments and understand what's going on in a small area that you're really interested in, and you can just all of a sudden you got graphic understanding of what's really happening inside of this complex computer model, and it really opens your eyes.
Too often the complex model that's proposed is just too complex because people are too lazy to understand what is really core to that predictive equation, what's going on there. That's kind of frustrating. But that's what happens when you let algorithm writers create these kind of predictions.
So let's swing the focus back to where we do have the data and where we can look at the design space. What are some lesser known designs that you think could be applied more broadly?
We're seeing definitive screening and OMARS designs coming out more, and there's lots of different kinds of OMARS designs that's being created, new ones coming out all the time. I'm still a little skeptical on using these, but I'm still trying to understand them. One of the things that we run into in industry is you sometimes lose data points. And so you can design a beautiful design, and if you lose a couple key data points, some of these really complex or designs like OMARS can be destroyed in a sense. You lose a lot of properties that you were trying to get in the first place by getting this nice design. And so one of the things about definitive screening that I've been definitely cautious about is the losing points. And you do lose points, or you try to hit a target temperature and you were not able to hit that target temperature for whatever reason. And there's things like that happen in reality out here in the industry. So you've got to be cautious. You like really robust designs. If you lose a point, it's not killing you, and you can go on. And that's very important to have as well.
Also the sequential nature, right? If you can keep a sequential design, you don't run into these pitfalls with some of these small run designs in DSDs. They're hard to use sequentially.
And sequentiality is important in building models correctly.
Well, I am quite interested in this definite screening design. I'll take a look on it. And space filling design seems to be a useful option based on, I completely agree with you, Arved. And I'll look at it in more details, but I think it's a really good option when we don't have an error, when we are working with computer simulations and not experimental data. If you use regular designs, we have problem even with a small error. We see that in analysis of variance, traditional analysis of variance, when we have very low pure error, we have implications of that. So I think space filling design will have space in the future.
The problem I've had with space filling designs is the algorithms typically tell you pick which kind of space filling design you want, and then tell me how many runs you want, and I'll give you the design. There's not many criterion around that. So it's hard for me to know, okay, I've got a 15 run design. How good is that compared to a 16 run design? I don't have a criterion.
How
So
good is that compared to an optimal design? This is a question that I have. If we compare both, do you have an answer for that?
Oh,
if
I
we
do not.
compare space filling design and an optimal design, any criteria?
What optimality criteria are you using? You know, that runs into this debate as well. How many different optimality criteria are there?
Right.
Bunches of them.
Amen.
As
If the assumptions aren't met, none of them
the
are
alphabet
optimal.
Ray Myers used to call it the alphabet optimality.
Amen.
Yeah.
Have you done that, Arved?
Looking at space filling designs compared to the D-optimal or optimal designs. Well, the thing about
Any
space filling
optimal design?
is not dependent on the model, whereas optimal designs are. So you choose based on the model. You've got a quadratic model or whatever, and then you try to choose a model or a design to fit that. Whereas space filling design is not based on a model. It's just, I got 5 factors, I've got my space, okay, fill it up with however many runs. So I know I've not done a lot of comparison of that.
I mean, especially related where the points are located. That's my question.
Already with those space filling designs, it's going to become more and more important to have the ancillary information available too. to refine that variability. You know, 'cause that's not, I don't ever see anybody talk about the ancillary data that are going to be collected by sensors that are not directly involved in the experiment itself. But on the other hand, that provides a huge step forward in eliminating the variability and getting better conclusions.
Oh, you had something you wanted to hop in and say? Or did it pass?
I was just trying to move from this to you know the need. We still have a lot of scenarios where we need to block resolution 5 designs. You know, the resolution 5 designs have not been utilized as they should. They wonderful screening tools, and they're good building blocks for future studies. But sometimes we are faced with a need to block nuisance factors, or what we can consider as nuisance, as in more than one direction. So, you know, it brings back one of the good old designs, the Latin squares, and we're getting, there is a need for these, but there is a very limited help from software side. I think these are, especially for us in traditional manufacturing, we always, especially composites, you know, you can't ignore variability along and across a panel of composites. That's something you know, we always see, even in sheet metal, when we talk about material that has been cold rolled or soft rolled or hot rolled. We still see variability along and across, and sometimes you need to control these to be able to see real effects. So I think that will not go away, and I hope it wouldn't, because it's useful arrangement for getting started or even getting to understand the real factors. Thank you.
We're also starting to see designs created for specific applications like nonlinear models, where you're expecting a particular kind of model based on knowledge, and you would like to collect which points do I need to be able to estimate these parameters best. That's we're seeing that more in software, and that's very, very helpful in the industry. And examples like even simple designs like MSA designs and DOE for life testing and things like that are some other great applications out there. There's many other specific applications where the DOE can be customized to the models that you're looking for.
That's the principle of optimal designs. The model
But
oriented.
optimal designs are usually for, we're thinking polynomial equations, and I'm saying we're
Yeah.
not always thinking polynomial equations.
Okay.
Something of interest to me, Harvard, along those lines, is the combination of nonlinear and linear. So the nonlinear would be going back to the basic scientific theoretical foundation, but then enhance that with, you know, Taylor series approximations on the residuals. That seems to have some real potential. Trying to get the best of both worlds in some sense.
All right, at this point, I am going to start inviting questions. If you have heard anything today that you would like to ask a question on, go ahead and throw it either into the question section or into the chat, and I will take a look and pose those to our panelists. As we're waiting for those to come in, do you folks want to plug anything that you have coming up? Any appearances you're making? Any talks that you think people should go see?
Highly recommend the Fall Technical Conference by ASQ and ASA. That's in Houston in October. That's always a good meeting, particularly for DOE.
All right, we have a question in How sufficient is the flow of new DOE leaders? What universities are taking the lead? So
Almost
where are you
none.
seeing the new knowledge
Uh,
coming out?
I'm
Actually,
sorry.
in the US, almost none. It's not popular anymore. Drew, am I unfair?
Well, it's getting more popular among mechanical and aerospace engineers. I feel like we've made some inroads and we're gaining in popularity. I can't speak to the statisticians.
Yeah, the stat side is not good.
Okay,
More and more programs don't even do it anymore.
that's sad.
One of the things Staties has been working on has been improving our presence within the academic sphere. So the idea of getting DOE back into universities, back into standard statistics education is one of our goals as the only DOE focused major software out there.
Rachel, I'm sorry, I had an internet problem here. I could not hear the question.
Oh, sure. How sufficient is the flow of new DOE leaders? What universities are taking the lead?
You mean the background of the leaders in the university?
Who's putting out new DOE thought people? Who's coming up with the new ideas?
Wow, that's a
More and
difficult.
more, it's going to come out of engineering and historic statistics departments because they're focusing more and more on machine learning and data science.
And development, yeah, academic statisticians probably, but I always think about the practical applications of DOE. I'm not really on the development of new methods, but I do think this should come from university. Sure.
Okay, next question. How process capability index is useful in designing?
Process capability.
That is the question.
Yeah, it's really useful, as I said, to determine the distribution of predicted responses and not only the average. We can use process capability methods to have this distribution, and then it helps us to build the uncertainty limits and to get a robust design space or MODR. So definitely process capability indexes can be used in the DOE with DOE models to predict a robust region to work. That's how I see it.
And what Marcia was showing earlier is exactly the kind of thinking that needs to go into the analysis when you think about your process capability. Kind of variation are you expecting to see in the response? That's a great way of looking at it. But also going in, you need to think about your test method variation and things like that. That is going in because many times you will find that you shouldn't be designing an experiment right now. You should be working to reduce the variation in your
Amen.
process before you start designing the experiment because you're just overwhelmed with too much variation. You're not going to see much signal above the noise if you run a DOE. So you've got to get a handle on that before you get into your designed experiment is what kind of capability do you have? What kind of signal are you looking for? Are you going to be able to see it?
A book that I would
I
highly recommend is Schuhart, 1939, a series of lectures he gave at the U.S. Department of Agriculture, edited by Deming. It's a classic. It talks about some of the things you were talking about, Arved. It's 4 chapters, but it's going methodically through. He takes its beginning with, statistical process control, but he's talking about all of the elements of uncertainty that you've got to deal with. And keep in mind, he was a physicist.
thank you, Dr. Vinning, for bringing this. I mean, process capability indices remind me of stability, and maintaining the status quo. What you need with design of experiments is to explore areas where you have never been operated at. I mean, you have to move factors outside the norm, up and low or whatever, to see how the process will react. So if CP is CPK or whatever index you have is tied up to the condition of the process being stable and with no unusual changes. But when you go down the road of design of experiments, you really have to push the envelope to be able to understand what sigma is, what are the factors that make up the total sigma you would consider in calculating your CP. What type of variability? It could be coming from a number of sources. It's only DOE that can help you break down the total to elements and understand which of the elements deserve your attention and efforts for reduction. I don't see how you can do this within norm. I mean, you have to really leave the envelope or your comfort zone to see what factors can cause changes or improvements. Thank you.
I could see the process capability as a great way to identify processes that need DOE. That they're borderline in terms of their capability, and then they become the targets for, okay, let's do a thorough study to improve it.
Yeah. I want to get to one more question before we wrap up because I want to respect everybody's time. There are a couple questions that won't get answered out loud, but I will put them to the panelists and have them sent out to everyone who attended today once we have some answers. The last one to do out loud, Paul asks about split plot designs. Does anyone have this experience that he can predict that the whole plots are not statistically significant because there's too few degrees of freedom? And all the split plot factors are statistically significant because there are too many degrees of freedom. Has that been your experience?
What it goes back to is doing hypothesis tests, and there's a better way of doing the analysis, trust me. I've got the battery example that I've given out in the notes is a split plot experiment. There are no hypothesis tests, so we don't worry about degrees of freedom. What we're doing is treating it as a regression problem and identifying what are important characteristics for prediction. And it works like a charm. So that's a problem with how we have dealt with things in the past, going back to agricultural origins, rather than trying to adapt for what is happening in the industrial world today.
Do you think that question was aimed at looking at factors that are involved, whole plot factors that are involved in interactions with subplot factors being significant, and then relating back to if they're found significant, not worrying as much about whole plot factors on their own? Is that what that question was?
Yeah.
There's no indication, but
I think so. I think that they are looking at, your whole plot. You don't have whole plot factors don't have a lot of power. But one of the things people are missing is that if, like you said, the fact that they interact with stuff that's not in the whole plot, you do have a lot of power there. But also recognize this is something, the default designs in a lot of software, the number of whole plots. If you would increase that 2 to 4 whole plots, you would be shocked at the number of how much power you gain on those whole plot factors. So sometimes you're using maybe using an optimal design of some kind, and it's coming up. But if you would push that number of whole plots up, I think you will find that your whole plot power will drastically go up. I'm working on one where I think I increased. It all comes down to your whole plot error degrees of freedom. If you look at your whole plot error degrees of freedom, you can get a good handle on how many you need to get some good power there.
And you don't have to use complete replication either. You might be able to throw in some extra whole plot centers or something like that to build up the degrees of freedom.
That's possible, yes.
All right. Thank you, everybody. Thank you to our panelists for coming and sharing their experiences and expertise today. Thank you to everyone who attended all the way through. If you are watching the recording, Thank you for watching the recording and taking advantage of this learning at an asynchronous time. If you have any questions for our panelists, you can send them to webinar@staties.com, and I will field them back to these folks. Again, Arved Harding, Drew Landman, Geoff Vining, Gamal Weheba, and Márcia Breitkreitz are here and celebrating Staties' 40th anniversary. Thank you, thank you, thank you all, and have a wonderful rest of your week.